Beep. Dear Heavenly Father, we thank you again for this opportunity we just have to meet together and to study your creation. Just pray that you'd guide our steps today, help us to glorify you what we do, and help us all just to understand a little bit more about conservative vector fields and their properties, Lord. In the name I pray, Lord Jesus. Amen. Let's see here. So, I've been talking a lot about conservative vector fields already, but I don't think I ever quite calmly and carefully wrote down the definition for you guys. Well, I might have, but we should write it again. So here's the definition. So today, at least for the first part of class, we're talking about conservative vector fields and their properties. And so I guess a definition is in order. Definition, F, all right, is a conservative vector field on U, a subset of Rn, if there exists f, little f, a mapping from U to the reals for which the gradient of little f is equal to f, big F, on U. All right. So there are lots and lots of conservative vector fields. I'll give you, let's just start out with an example. Example 1. If I had, f equal to, I don't know. I'll keep it really simple, x, y, z. Right? I can easily see that that's the gradient of 1/2 x squared plus 1/2 y squared plus 1/2 z squared. Right? So it's a conservative vector field. Where? Well, on R3, right? So here's my potential function f, right? And for instance, if I wanted to calculate the line integral, right, from the point, say, x naught, y naught, z naught, to the integral, to the point x1, y1, z1 of f dot dr, what would it be equal to? Or, in fact, let me just slip back into the other notation for a second here. X dx plus y dy. I mean, I'd like for you guys to be comfortable with both notations. The f dot dr notation, right? But also this differential notation, if you will. And so fundamental theorem for calculus for line integrals says, well, that's 1/2 x squared plus y squared plus z squared. I factored the half out. Evaluated from, x naught, y naught, z naught to x1, y1, z1. Right, so the answer here would be 1/2 parentheses, x1 squared plus y1 squared plus z1 squared minus 1/2 x naught squared plus y naught squared plus z naught squared. Which, as I was, talking about yesterday, is pretty cool because, that's a pretty neat situation, right? You got this point, x naught, y naught, z naught. You got another point over here, x1, y1, z1, right? And you notice I've introduced a notation. I've introduced a notation that we can denote the line integral from one point to another just by the endpoint and the starting point. When is this logical, though? This only would make sense when there is no dependence on which path you're taking from one point to the other, right? But that would be the case here because the fundamental theorem of calculus for line integrals says it doesn't matter if I do this path, right? Or if I do that path, right? Either way, the answer would still just depend on the value of the potential function at the beginning and the ending point, right? And this one, there's none of the distractions of the example yesterday with the tangent, right? Because the domain for this thing is all R3. Any questions? No? All right. So an obvious question is, why are we calling it a conservative vector field? Where does that terminology come from? It's not politics, if you even can define what conservative means anymore. But which kind? Paleo, neo, whatever, so many kinds. But let's see here. So if you've got the force and it's equal to the mass times the acceleration, and so here acceleration is equal to the change in the velocity with respect to time t, right? dv dt, this is the velocity, the acceleration. Well, then we can calculate the work done in this situation. What's the net work done? See, this would be the net force. If we say F is equal to ma, then that makes that the quote-unquote net force, right? The total force acting on the mass. And if we calculate the work done along the equations of motion, so if we integrate along, let's say, C, where C is the solution of Newton's equations, calculate the work done in this situation, well, then we've got the integral from, say, time 1 to time 2 of, well, what is that? F is equal to what? F is equal to ma. So m dv dt, right? That's the force. But what was the formula for the work done? We do the force dot the velocity integrated. So, you know, we do dot dr dt, right? Definition of line integral dt. Just going back to the definition that we've been talking about this week. But then there's a kind of neat trick you can do here. You see, this is equal to the integral from t1 to t2 of the total derivative of 1/2 m v dot v dt. Now, this may not be obvious at first glance. So let's see here. What we're looking at is m dv dt, right, dot v. That's the starting point, right? What happens if you differentiate this? I don't really want to write it out, but let's think about it in our mind. What happens when we differentiate a dot product? With a product rule, right? So when you differentiate v dot v, you get dv dt dot v plus v dot dv dt. But the dot product is commutative, so you get two of them, right? So we get 2 times this by differentiating the thing without the half. So if we divide by half, this is just an identity. What's here is equal to what's there, all right? They're just literally equal. But now, we've got the integral of a total derivative, which means this is what? 1/2 mv squared evaluated at t2 minus 1/2 mv squared evaluated at time 1. And so in physics, we call this quantity 1/2 mv squared the kinetic energy, right? So what this says is kinetic energy at time 2 minus the kinetic energy at time 1, it's equal to the work done. Yep. That's v. So if you just calculate the derivative here, we get dv dt dot v. See, this is v. And then plus v dot dv dt, which is again this because it commutes. So that's the one thing, is this is called the work energy, the work energy theorem. The work energy theorem says that the work done by the net force is equal to the change in kinetic energy. This right here has nothing to do whatsoever with conservative force. This is also true if your total force was a friction force or whatever. This is just a consequence of what? Newton's law. See, all that this is derived from is just assuming F is equal to ma. That is only true for the net force. All right? If you just had one force in a sea of many, this wouldn't be true. All right? True for the net force, because the net force is the one for which F is equal to ma. But if in addition, we also know if the net force is equal to minus the change minus the gradient rather, and let's say, I don't know, I need a letter here. I guess I'll use U. We usually use U is equal to potential energy in physics. Potential energy. And the reason for the minus will become apparent in just a second. But that's a convention to put a minus here, okay? And then you calculate the integral along the curve, the same curve we were just talking about, of F net dot dr. And it's equal to the integral of minus the gradient of the potential energy function dotted with dr over the curve, which by the fundamental theorem of calculus part 2 is minus u of, time 2, minus a minus, which would be plus u of time 1. Or if you want me to use the usual physics notation that I like this notation in physics, minus potential energy 2 plus potential energy 1. But these are equal, right? In other words, these are two different ways to calculate the net force, the work done over the situation. So those are equal, which tells you what? It tells you kinetic energy 1 plus potential energy 1 is equal to kinetic energy 2 plus potential energy 2, which is to say that the energy at time 1 is equal to the energy at time 2, where we define the total mechanical energy to be the sum of the potential and the kinetic energy. And that's why it's called a conservative force, because in the presence of a conservative force being your net force, if the conservative force is the entirety of the force acting on a mass, then we can define this quantity called energy, and the energy is constant over the motion. So that's why it's called a conservative force. It's from physics. But conservative forces are interesting just for their mathematical properties as well. So any questions? All right, so let me give you a the big theorem, if you will. So here's, no, I'm not sure I should write it here. I'm going to write the theorem over here, so I can do the proofs in the middle board. Proposition. Suppose U is open, connected, subset of Rn, the following are equivalent. Number 1, F is conservative on U. Number 2, F is path independent on U. Now I probably should define path independent. I defined it right above this proposition. This is proposition 7.45 in the notes on page 337. Path independent, what this means is that let me just kind of draw a picture. So here's a picture of U. I may or may not have told you I had a friend in graduate school who she used to say that she was trying to become perfectly spherical, because if she had perfect spherical symmetry, that would be the highest form of beauty. She was a physicist. Now she wasn't actually that fat, but this would be as close to her ideal, close. Close, but not quite there. Anyway, so path independent means that if you pick 2 points, initial point, final point, right? And you've got any curve like here and like there, whatever, say C1 and C2, they could cross each other. The point is that they're just two paths which begin at the same point and end at the same point. You could say these are 2 coterminal paths. Coterminal. Same beginning and ending points. Then path independence of f means that the integral of f along C1 dr is equal to the integral of f along C2. This is path independence. Not just for one pair of paths, but for all possible pairs of paths, all possible coterminal pairs in your open set. That's a lot, right? It's a lot of paths. But that's the concept of path independence, is to calculate the work done from one point to another, it does not matter which path you take, you get the same work. Like my example 1, right? That has path independence because it only depended on the endpoints, right? Now example, listen to me. Point number 3 here is that the integral around a loop is equal to 0 for all, so this is for all closed curve. C subset of U, all right. So I would generically refer to a closed curve as a loop. That may actually be, that's probably a little bit more special. I think typically maybe a loop wouldn't include self-intersections. For me, a closed curve, an example of a closed curve, what does a closed curve look like? So here's some closed curves. This is a closed curve, all right? That's a closed curve. I would also call that a loop. But something like a figure 8 would also be a closed curve. All right? It's got no, how to say it. I don't know. I don't even want to try to define it carefully. I mean, is the picture okay? Do you guys see what I mean by closed curve? It starts where it begins, right? It's got the same starting and ending point ultimately. It can be parametrized in such a way that it begins and ends at the same point. We could define that. That's what a closed curve is, okay? And then point number 4, and this is the slightly tricky one, is that, and here we specialize, okay? Here we add precondition. Here we add precondition n equals to 3 for the dimension, and U simply connected. So we add that assumption. All right. In view of that assumption, we can put on the list the curl of f is equal to 0. Now, let me point out, like, there's an easy theorem to see here, right? Theorem, if f is equal to the gradient of f, then the curl of f is equal to the curl of the gradient of f, and remember, that is 0. The curl of a gradient is 0. So it is always, it is just generically true that 1, right? Proposition, point number 1 implies point number 4. This is true, what I just wrote in purple, independent of any sort of topological assumption, any sort of assumption about the simple connectedness of U. It's the other direction. It's assuming that curl of f equals to 0 implies there exists a potential function. That's the subtle direction. So we'll have to return to, that's the last thing we'll do on this list, okay? 4 implies 1, essentially. Okay, so let's get to it. Let's prove these things. And because the proof is actually not that hard, let's get to it. So let's look at 1 implies 2. How can we do that? F is conservative on U implies F is path independent. This is pretty much my example 1, right? So if F is equal to the gradient of little f on U, and C1 and C2 are coterminal paths, from point P to point Q, then what? The integral along C1 of f dot dr is equal to the integral of the gradient of f, right, along C1 dot dr, which by the fundamental theorem of calculus for line integrals is f of q minus f of p, right? But hey, that's equal to the integral along C2 of f, of the gradient of f dot dr, which of course is equal to the integral of C2 of f dot dr. And therefore, f is path independent. So proof that 1 implies 2 is like shooting fish in a barrel. Right? That one's really easy. I don't think I ever get stuck on this one. All right. Now, how do you prove the equivalence of 4 things? Logically, you've got different choices, right? Like, one way you could do it is prove 1 implies 2, 2 implies 3, 3 implies 4, and then if you can prove 4 implies 1, you actually get the equivalence of all 4 statements. Because if you can circle back, then you can get 2 implies 1 by going 2 implies 3 implies 4 implies 1 implies 2. So if you can actually circle back. But what I usually do here is actually just prove the equivalence of each pair, because there's value in seeing. So like the proof I'm giving you is not logically minimal. That's what I'm trying to say. But I think it's helpful because you'd like to understand how it is that 2 implies 1. But actually, we're going to come back to 2 implies 1. We're going to put off 2 implies 1 for now. That one's harder to prove. Okay, I want to do the easy ones first. 2 implies 1 is actually a little bit subtle, but it's interesting. Let's see here. Can you guys tell me how to do 2 implies 3? Let's look at 2 implies 3. So these are all direct proofs. How does a direct proof work? You Math 200 people, you assume what? Assume 2 true, right? You're like, it's 2 true. I guess you didn't say that. Like only you would say that. That's true. Sorry, too many puns here. So we're assuming f is path independent, all right? Consider a loop in U, right? Then what does that mean? If I have the picture something like this, right? Here's my U. If we have a loop, what's it look like? Something like this, right? There's my loop. Let me call it C. Now what can I do? How about this? Pick any 2 points. Can you do that? I think that's a reasonable thing to do. Pick a point P and a point Q. Actually, my bad. I need to think about what I'm trying to prove. I'm trying to prove 3 implies, what am I doing? Yeah, 3 implies 2. What am I doing? Oh man, I'm sorry, I lost track. 2, I'm assuming 2 is true. Oh yeah, consider a loop. My bad. So here's my loop. Oh, sorry, the proof of 2 implies 3 and the proof of 3 implies 2 is almost the same. So if I forget where I am, I'll get sucked into the other proof. Okay, so anyway, I've got my loop. I picked 2 points, P and Q, right? And then what? Well, the loop had to be what? It's either, let's suppose that the loop was what? Like counterclockwise oriented? Yeah? So the loop, that means it did what? Like this direction, right? Okay, so let's see here. Let's say the lower half of the loop is C minus, and the upper half of the loop is C plus, right? So C is equal to, like C minus union with C plus, right? Now look at this. C minus is a path that goes from P to Q. C plus is a path that goes from Q to P, right? But we can do what? We can reverse C plus. We can look at the reversal of C plus, and that would be a path that goes from P to Q, right? So that's called minus C plus, right? That's our notation. And so you see that C is actually, C minus union with minus C plus, right? Well, excuse me, that's not what, I'm an idiot. Oh, sorry. All right. Now we're assuming that 2 is true, which means we're assuming what? Path independent, right? So my observation is this. C minus and minus C plus are coterminal, right? So that means that the integral of f dot dr along C minus is equal to the integral of minus f dot dr along minus C plus, right? But by the properties of line integrals, right, if we reverse the curve, we pull a minus out, right? So this is equal to minus the integral along C plus of f dot dr, using our little theorem that if we reverse the curve, it changes the sign of the line integral, all right? It's an oriented integral. So then what? So what, and how did I get to say this is equal? This is what? Thus by path independence. Since 2 true, right? We're assuming 2 is true, path independent, so we have equality of those. And then you just put it to the other side, and we've got the integral along C minus of f dot dr plus the integral along C plus of f dot dr, which is, by the way, the integral of C minus union C plus of f dot dr, which is, of course, the integral along the curve of f dot dr. And that was all equal to 0, right? So I mean, I feel like I could start with a 0 over here. Thus what? Thus 3 is true. Okay? Now let me just talk for a second about 3 implies 2, unless there's a question. Now I sometimes think that 3 implies 2 is just literally the same argument in reverse, but that's not quite true, because what on earth? Why is it so high? Way up there. If I have two coterminal paths, like so 3, I'm assuming the 3 implies 2. I'm assuming that the integral around all Well, see, I guess if I assume the integral around all closed curves is equal to 0, right? Well, the closed curve doesn't have to... I'm sorry, I've lost my train of thought. Well, I don't know. Maybe I'm wrong. Maybe it is just that simple. I guess the thing I tricked myself into is thinking that the picture is always just that. The picture could look like, if I have two coterminal paths, right? If I've got a path P and a point Q, and I got like two coterminal paths, I'll do the one in blue. You know, it could look like that, right? This could be C1. And maybe C2, right? Maybe C2 looks like this. Like that, yeah? C2 could look like that, couldn't it? So those two paths are both coterminal. Now I'm assuming that the integral, what is it?
They can intersect?
Yeah, they could intersect. Yeah. That's the thing, is they could intersect. I've been drawing the picture like they don't, but of course they could. That's not prohibited. Definitely these are still coterminal paths, right? They have the same beginning and ending point, so they're coterminal paths. And if I'm assuming 3 is 2, I'm assuming that the integral around a closed curve is 0. Well, I think there's also clearly a closed curve here, right? What's the closed curve? Basically, the closed curve is simply what? Say that again?
Union of C1 and minus C2.
Yeah, union of C1 and minus C2, that's right. So if we do, just like you said, if we do C1 and then minus C2 like that, we begin and end at the same point P, right? So therefore, the integral along C, by assumption of 3, is 0. But if the integral along 3 is 0, I think you can see, well, it's this calculation right here, right? If we know that the integral along C is equal to 0, and we know that C is formed by the union, I'll just write it out. It's easier to write than to talk through. Integral of f dot dr C equals to 0 implies the integral along C1 of f dot dr, plus the integral along minus C2 of f dot dr is equal to 0, which then implies that the integral along C1 of f dot dr is equal to the integral along C2 of f dot dr. There you go. Again, it rests on the orientation property that if we reverse the curve, it changes the sign of the line integral by minus, all right? So there you go. There's the proof of 2 if and only if 3. I would say in some sense the proof is essentially topological. It's just these pictures almost. There's really not much to it other than that. And again, the proof that all right, so to get the connection between 3 and 4, like to prove 3 implies 4, the easiest way to do that is that 3 implies 2, and 2 implies 1. And so let me just put this logically. So if 3 is true, then 3 implies 2 implies 1 implies 4. Now, at this point, at this stage in the game, what have we? The one thing we've not done is what? Well, there's two things, right? We haven't done this yet. We haven't shown that 2 implies 1. All right. And we also, of course, have not shown that if we add the precondition, we can get that 4 implies 1. That we're doing last. All right, we're saving 4 implies 1 for the last. again, with the simple connected tacked on in that case. Now 2 implies 1 though we should do now, and this one actually is, this one requires some careful argument. I would say this one's not altogether obvious. So I need a fair amount of board space for 2 implies 1. Can I erase all this actually? Because we're done with it. All right, so we're going to assume f is path independent. All right, and so we need a kind of nice big old picture. Here's my picture of U. U is open. That essentially means it's got a fuzzy edge. All right. It's connected. That means that you can connect any 2 points with a path, right? So the construction goes something like this. Pick a point. Let's say A. All right, so we pick a point. A in U. All right. And then I'm going to define, and then we let C be any curve from A to B, where B is equal to x, y, z. All right? So there's B. And basically, we'll say f B is equal to x, y, z. I'm trying not to, I'll put it over here. B is equal to x, y, z. And then we let little f of x, y, z equal to the integral from A to B of well, let me say from A to x, y, z of f dot dr. That makes sense because we're assuming path independence, right? So it doesn't matter under the assumption of 2 is true which path we take from the reference point A, all right, to the point B where we're trying to construct the potential function. So this is how we construct the potential function actually from the integral. So then what we're going to do in order to understand the property, so a little bit more notation here. We're going to let f equal to PQR for the sake of the discussion, all right, just to give the components letters names. And so we're going to begin by isolating the x component. What we need to do, what's our first goal? Our first goal is to show that the partial derivative of f with respect to x is equal to what? P, right? If this is right, if this is a legitimate potential, it's got to be such that the gradient of this is giving me back my force, right? So I need to show the partial derivative of this with respect to x is P. In order to calculate that partial derivative, it's important to take a curve that explores the change in the function in the x direction near the point. So what you do is fix y and z and take a little line segment here, like that, right? And this is L sub x. And then, you know, you got your whatever over to there. So let's see here. Let me give these things some names. Oh, my bad. I wanted to let, just a second. I got to be careful. If I draw the picture wrong, I'm going to get confused. I wanted to have x naught to be less than x. So my picture is not quite true to my calculation. So since it's open, we can bring in this horizontal line. Let me draw it in red. I can bring in a little red line segment like that from the left, right? I mean, correct. Now, and then of course there's this. Let me draw this other one in a different color. From A all the way over to that point, like that. I got that point, that curve. Now, let me give these guys some names and tell you what's going on more completely here. So this point right there is, so the point B is x, y, z, right? But this point right here is going to be x naught, y, z. And we're assuming that x naught is less than x. All right? So the trick here, a little trick, is that the blue curve, which I have a name for, I'm trying to remember what it was. My name was CX for that. The funny thing is, actually, maybe I should call it CX naught. All right, I'm going to call it CX naught because the truth is that you notice that the blue curve actually doesn't depend on x directly. It depends on the y and the z for your point, but the x naught is not, it's independent from x. It could be 0.1 units to the left, it could be 0.5 units from the left, it could be I don't know how far it is from the x to the left. It's independent. This x naught is independent from that x. Do we agree? This is kind of important because the whole proof really hinges on this observation. All right? So good? All right, so if we calculate then the potential here, f of x, y, z, right? It's equal to the integral of what? Of cx naught, right? Of f dot dr plus the integral over Lx of f dot dr. But notice that partial f, partial x is just going to be partial x of what? Lx, right? Why? Because again, there's no x dependence to the curve, the blue part. The blue part has no x dependence. So when we vary x a little bit, right? If we change x a little bit, and don't change and fix y and z, if we just vary, you know, this point a little bit, it doesn't change that integral. Okay, so then what? Well, then we just calculate what explicitly is the integral. What is explicitly this integral? How do you parameterize Lx? Guys, tell me. What's the parameterization of Lx? We can look at R of t equal to what? You got x. So you got t for x, all right? And your y and z, well, they're fixed at y and z, whatever those are, right? So, in other words, you've got x equals to t you've got y equals to, well, anyway, so the point is here that dr dt is what? 1, 0, 0, right? And this is for what? What's the parameter range here? If we're using x as the parameter, it goes from what? From x naught to x, where x is fixed. So x naught less than or equal to x, my bad, x naught less than or equal to t less than or equal to x, right? So explicitly then, this is partial x of the integral from x naught to x, right? And then we've got f of, you know, t comma y comma z dotted with 1, 0, 0 dt. What is that though? That's the integral from x naught to x of p of t y z dt. Right? Because we just, when we dot product with 1, 0, 0, we only pick up the p component, the x component. Look at what we're doing. We're differentiating with respect to x holding y and z fixed, the function p of what? T comma y comma z, right? What is that? Well, the fundamental theorem of calculus part 1 says that it's just equal to the integrand evaluated at the upper bound, because this is in fact a total derivative with respect to x, right? Understand that this partial derivative is a total derivative in this context. Just setting y and z fixed, we can apply fundamental theorem of calculus part 1 from calc 1, and lo and behold, we get p of x, y, z. Aha! Thus, partial f, partial x is equal to p. Do you guys understand the argument? If you understand the argument, how would I do it for q? What should I do to get partial f, partial y to show partial f, partial y equals to q? What path do I need to consider? Say again?
F of x, t, z.
F of x, t, z. Yes! And how would I get that from a path? I would do something like, maybe like this, right? Oops. Like that. Come into here. This point would be x comma y naught comma z, right? And run a vertical line segment from there into the point, right? Like an L sub y, let's say. And going through the same argument, the partial f, partial y would not depend on the purple curve. It would just depend on the vertical line segment. That's the only thing that has the y dependence. And I do mean y, not y not is a y, but it's not y. I know. I got confused about this once upon a time in my life, but you know, the y and the y naught are independent. Now, certainly x and z are dependent. The x and z definitely matter. To set up a vertical line segment from the given point x, y, z, we do have the same x and z for the green line. Green line does depend on y, on x and z, but it does not depend on y. Okay, so anyway, looking at that path, we can show that partial f, partial y is equal to q. Because, yeah, we'll have partial y of the integral from y naught to y of q of what you just told me a second ago here, x, t, z. You're exactly right. That's where the end point of that argument ends up, and that is equal to q of x, y, z. Exactly that. Say again?
Is your point that the line that goes through those 2 points
Mm-hmm.
isn't a function of
Now, which 2 points?
B and the one where L line goes to?
B in the purple point?
Is that it's not a function of the y value of B?
Yeah. Not now. The green one does. The green one depends on y, but the purple one does not. The purple one only depends on y naught. See, and I could move y naught up and down, but that would not move this point. I've picked this point. It's fixed throughout the discussion, and I can move this around, not any which way, only up and down for this part of the proof, because there I have to fix the x and the z for that line segment to be vertical. But you see, I could put this purple point real close to the point B, or further away. Now, up to a point, of course, because I'm up against the edge of the U, but that's that.
What in particular is moving it, not changing?
What's that?
What in particular is moving that point, not changing?
What I'm saying is I can vary y naught without varying y. What I'm claiming is that my claim of independence of y naught and y is a reasonable one, because I can independently, I can fix B, and I can move the purple point up and down without moving the B point. Likewise, I can fix B, and I can move the red point over here back and forth without moving that point. So the x and the x naught are independent. Right? Now, I have engaged in fuzzy thinking before with this, and I thought, well, they're both x, so they're both dependent because they're both x. But that's fuzzy thinking. That's not what we mean by independent. Independence means that you can change one without changing the other, and we can do that. And the same for, now I don't want to picture it, but you see we could do the same for an up and down, a z curve, right? And so we'll also get that partial f partial z is equal to r, right? Therefore, this indeed is a construction of the potential for a conservative force. This proof is actually very interesting because it gives us a method for calculating the potential for a conservative vector field by integration. Do you see that? So like lemma, if f path independent and on U, and A, well, let's not even say A. Well, yeah, fine. A is an element of U. Then, you know, f of R equal to the integral from A to R of f dot dr has nabla f equal to f, right? Now, this is just what we proved. This is the proof. Do you want to take this for a spin? Let's see how it works on my example 1. Can we actually calculate? Can we calculate this formula that I just straight up guessed in example 1 from an integration? Can we do that? Let's try it. See if we can do it. That looks simple enough that I probably can hack through it. Let me see if I've got time. So let's see here, example. Man, what example am I on? 2? Okay. Yeah, a lot of proofs today. Oh well. All right, so let us define f of x, y, z equal to the integral. And I think we should use the origin as our a. Does that make sense? That's the easiest thing. So we'll get integral from 0 to xyz of f dot dr. And okay, so how do you actually put this into practice? Actually, guys, let me not do xyz, the vector field, because it's too much like everything else here. Let me change the vector field a little bit, make it a little bit more ugly, so that we can see the difference between what we're doing. Let me just add squares here. I think that will make it. Now, okay, so admittedly, I'm no longer with my example 1. But I think it's for a good cause, because then you'll be able to see the distinction between. It's going to help. So here's my point xyz. Here's my origin A. I need to calculate this. I'm claiming path independence. Admittedly, I haven't proved that. But I can rest on the rest of the proposition. You can easily check that the curl of this is 0, therefore it's path independent, once you accept the totality of the theory here. All right? So since the curl is 0 on all of R3, which is simply connected, it's path independent, hence conservative. Therefore, this construction is going to work. So anyway, how about this? A line. So I would suggest we use R of t is equal to t times xyz for 0 less than or equal to t less than or equal to 1, right? That is a nice parameterization from the point 0 to the point xyz, where here xyz is fixed, all right? And so what we got? We've got the integral from 0 to 1 of f of tx, ty, tz, dot product with derivative of tx, ty, tz. All right, dt. And what is that? Well, the f, so I'm going to have myself a t squared, x squared, t squared, y squared, t squared, z squared. That's what happens when I plug tx into x and I plug ty into y. I plug tz into z. I had to square the x, the y, and the z respective. This is why I changed it to square, so that you could appreciate the process of what we're doing. My example 1, it's too simple. It's going to deceive you if I do this calculation. So I wanted to uglify it a little bit. Mission accomplished. But this, on the other hand, what's the derivative with respect to t? Keep in mind, throughout this whole calculation, x, y, and z is a fixed but arbitrary point. All right? So this is just what? X, y, z. Take the dot product, what you got? We got ourselves t squared, x cubed, plus t squared, y cubed, plus t squared, z cubed, dt, which of course we can trade out for x cubed plus y cubed plus z cubed times parentheses integral from 0 to 1 of t squared dt. This is not in my notes, by the way. Not really. This should be in my notes, but it's not. Another failing of my editor. So this right here, guys, is what? This integral you shouldn't actually have to do. You should just see the answer to this without writing it down. What's the answer? 1/3, right? So the answer here is 1/3. X cubed plus y cubed plus z cubed. And much like the integral I just said you should write down, this is a potential function that you ought to be able to just write down also.